Good morning, everyone. I am Renzi F. Felipe, your presenters for today. In this session, I am going to discuss about the derivatives, the definition of derivatives, the derivative of polynomials and exponential functions, the product and quotient rules, the derivatives of trigonometric function, the chain rule, implicit differentiation, the higher derivatives, the derivatives of logarithmic function, and rates of change applications related rates. First, we need to define what is derivative. Derivative in mathematics, the rate of change of a function with respect to a variable. Derivatives are fundamental to the solution of our problems in a calculus and differential equations. In general, scientists observe changing system, dynamic system, to obtain the rate of change of some variable of interest. Incorporate this information into some differential equation and use integration techniques to obtain a function that can be used to predict the behavior of the original system under diverse conditions. The derivative is the exact rate at which one quantity changes with respect to another. Geometrically, the derivative is the slope of the curve at point on curve. The derivative is often called the instantaneous rate of change. The derivatives of a function represent an infinitely small change the function with respect to one of its variable. It's written as dy over dx. Derivative of a function, also written as f of x, is equal to the limit of f quantity x plus derivative x minus f of x over derivative x as derivative x approach 0. I have note here that dy over dx does not mean dy divided by dx, except when it is convenient to think of it as division. While df over dx does not mean df divided by dx, except when it is convenient to think of it as division. We have here dx does not mean d times x, and dy does not mean d times y. I have here example, find the derivative of a function given using the formula f of x is equal to 3x squared plus 12. By substitution, the limit of 3x squared plus 6x derivative x plus 3 of derivative x squared plus 12 minus 3x squared minus 12 over derivative x as derivative x approach 0 is equal to the limit 3 quantity x plus derivative x squared plus 12 minus 3x squared plus 12 over derivative x as derivative x approach 0 is equal to the limit 6x derivative x plus 3 times derivative x squared over derivative x as derivative x approach 0. We have here cancellation of derivative x. Limit of 6x plus 3 derivative x as derivative x approach 0. Let derivative x as equal to 0. Then, the limit of 3 x squared plus 2x derivative x plus quantity derivative x squared plus 12 minus the quantity 3x squared plus 12 over the derivative of x as derivative x approach 0. So, the answer of f of x is equal to 3x squared plus 12 is equal to 6x. I have here the application of derivatives in real life situation. We have here the automobile. How it be? In an automobile, there is always an odometer and a speedometer. These two gauges work in tandem and allow the driver to determine his speed and his distance that he has traveled. Electronic versions of these gauges simply use derivatives to transform the data sent to the electronic motherboard from the tires to miles per hour or the mph, and distance or the kilometer. Next is the business. In the business world, there are many applications for derivatives. One of the important application is when data has been charted on graph or data table such as Excel, as you can see in the example. Once it has been input, the data can be graphed, and with the application of derivative, you can estimate the profit and loss point for certain ventures. Next topic is the derivative of polynomials and exponential function. In derivatives of polynomials, we have the power rule for whole number and the linear combinations. And in derivatives of exponential function, we have the by experimentation, the natural exponential function, and the final examples. In derivatives of polynomials, we have a fact that let n be a positive whole number, then the quantity x plus h to the nth power is equal to x to the n plus nx to the n minus 1 power h plus stuff with at least 2 h's in it. The proof, we have the quantity x plus h to the n power is equal to the quantity x plus h multiplied by the quantity x plus h and so on. Each monomial is of the form c sub k x to the power of k h to the power of n minus k. The coefficient of x to the n power is 1 because we have to choose x from each binomial, and there's only one way to do that. The coefficient of x n minus 1 to the power h is the number of ways we can choose x n minus 1 times, which is the same as the number of different h's we can pick, which is n. We have here the power rule. Power rule, let r be a positive whole number. Then d over x to the r power is equal to rx to the r minus 1 power. We have the proof as we showed above. The quantity x plus h to the n power is equal to x to the n plus nx n minus 1 h plus stuff with at least 2 h's in it. So, the quantity x plus h to the n power minus x to the n over h is equal to nx to the power of n minus 1 h plus stuff with at least 2 h's in it over h is equal to nx n minus 1 to the power plus stuff at least 1 h in it. And this tend to n x n minus 1 as h approach 0. The power rule for constant. The theorem, let c be a constant, then d over dx, c is equal to 0. Kind of like d over dx, x to the 0 power is equal to 0x to the negative power. Negative 1 power. Although x approach 0x, the negative 1 is not defined as 0. The proof is let f of x is equal to c, then f of quantity x plus h minus f of x over h is equal to c minus c over h is equal to 0. So, f prime of x is equal to the limit of 0 equals 0 as h approach 0. We have here the new derivatives from old. This is where the calculus starts to get really powerful. First is the adding function or the sum rule. Let f and g be function and defined. The quantity f plus g of x is minus f of x plus g of x. Then, if f and g are differentiable at x, then so is f plus g, and the quantity of f plus g prime of x minus f prime of x plus g prime of x. Succinctly, f plus g prime minus f prime plus g prime. We have the proof here. that the quantity f plus g prime of x is equal to the limit of the quantity f plus g times the quantity x plus h minus the quantity f plus g times x over h is equal to the limit f of the quantity x plus h plus g times the quantity x plus h minus the quantity f of x plus g of x over h as h approach 0. We have here the limit f of x plus h minus f of x over h, where h approach 0 plus the limit of g, the quantity x plus h minus g of x over h as h approach 0 is equal to f prime x plus g prime of x. Note the use of sum rule for limit, since the limits of the difference quotients for f and g exist. The limit of the sum is the sum of the limits. Next is the scaling functions theorem, or what we call the constant multiple rule. Let f be a function and c a constant. Define the quantity of CF multiplied by x is equal to CF times x. Then, if f is differentiable at x, so CF and CF prime x is equal to CF prime of x. Succinctly, CF prime is equal to CF prime. We have the proof here. The quantity CF prime of x is equal to the limit of quantity CF times the quantity x plus h minus the quantity CF times x over h as h to 0 is equal to the limit the CF times the quantity x plus h minus CF of x over h as h to 0. The limit is f of quantity x plus h minus f of x over h as h to 0 is equal to CF prime of x. Example of derivative polynomials. Number 1. Find d over dx times the quantity 2x cubed plus x to the fourth minus 17x to the 12 plus 37. We have here the solution. D over dx times the quantity 2x cubed plus x to the fourth minus 17x to the fourth plus 37 is equal to d over dx 2x cubed plus d over dx x to the fourth plus d over dx times negative 17x to the 12 plus d over dx times 37. As you can see, d over dx distributed is equal to 2 d over dx x cubed plus d over dx x to the fourth minus 17 d over dx x to the 12 plus 0 is equal to 2 times 3x squared plus 4x cubed minus 17 times 12x to the 11 is equal to 6x squared plus 4x cubed minus 204x to the 11. We have here the derivatives of exponential function. The theorem, let a is greater than 1 and let f of x is equal to a to the x. Then, f prime x is equal to f prime to the 0 f of x. We have the example here. Let f of x is equal to 2 to the x power. We have the f prime 0 is equal to the limit 2 to the 0 plus h power minus 2 to the 0 over h as h approach 0 is equal to the limit 2 to the h power minus 1 over h as h approach 0. F prime of 0 is equal to 0.6931747. The natural exponential function. We have here, if a is equal to 2, d over x, a to the x, as x equals 0 and less than 1. If a is equal to 3, d over dx a to the x as x equals 0 and greater than 1. We would hope there is a number a between 2 and 3 such that d over dx a of a to the x as x is equals to 0 and 1. We call this number e. Then by definition, d over dx e to the x power is equal to e to the x power. We have example here. Find d over dx, the quantity 4x squared plus 1 over x plus 3 to the fourth root of x plus 6e to the x power. Remember, 1 over x is equal to x to the power of negative 1. And the fourth root of x is equal to the x to the 1/4 power. So, dy over dx is equal to 8x minus 1 over x squared plus 3/4 x to the power of negative 3/4 plus 6e to the x power. Next topic is the product and quotient rule. The product rule, we have shown that if u and v are functions, that the quantity u plus v prime is equal to u prime plus v prime. And the quantity u minus v prime is equal to u prime minus v prime. What about uv? Is the derivative of a product the product of the derivatives? The answer is no. Try this with u is equal to x and v is equal to x squared. Then uv is equal to x cubed. Well, uv prime is equal to 3x squared. But u prime v prime is equal to 1 times 2x is equal to 2x. So we have to be more careful on that situation. Next is the product rule. Theorem, the product rule. Let u and v differentiable at x. Then, the quantity uv prime of x is equal to u times x v prime times x plus u prime times x v times x. In Leibniz notation, d over dx times uv is equal to du over dx times v plus u du plus du over dx. The example here is apply the product rule to u equals x and v equals x squared. The solution is the quantity uv prime times x is equal to u times x v prime of x plus u prime of x v of x is equal to x times the quantity of 2x plus 1 times the x squared is equal to 3x squared. This is what we get the normal way. I have here the example. Example of the quotient rule. But before that, we can discuss the quotient rule. Let u and v be differentiable functions and let q is equal to u over v. Then, u is equal to q v. If q is differentiable, we have u prime is equal to q v quantity prime is equal to q prime v plus q v prime, where q prime is equal to u prime minus qv prime over v or equal to u prime over b minus u over v times v prime over b. Q prime is equal to the quantity u over b prime is equal to u prime v minus uv prime over v squared. This is called the quotient rule. Example is, verify the quotient rule by computing d over dx times the quantity x squared over x and comparing it to d over dx times x. The solution is d over x times the quantity x squared over x is equal to x d over x times x squared minus x squared d over x times x over x squared is equal to x times 2x minus x squared times 1 over x squared is equal to x squared over x squared is equal to 1 is equal to d over dx times x. We have here the derivative of trigonometric function. When we say derivative of trigonometric function, it consists of the secant, the cosecant, tangent, the cotangent. I have here the derivatives of trigonometric functions. But before that, let's first discuss the example of derivative of secant. Find d over dx secant x. D over dx secant x is equal to d over dx times the quantity 1 over cosecant x is equal to cos x times 0 minus 1 times the quantity negative sine x over cos squared x is equal to sine x over cos squared x is equal to 1 over cos x times sine x over cos x is equal to secant x tan x. While in derivative of cosecant, we have here the example, find d over dx cosecant x. D over dx cosecant x is equal to d over dx times 1 over sine x is equal to sine x times 0 minus 1 times the cos x over the sine squared x is equal to negative cos x over sine squared x is equal to negative 1 over sine x times cos x over sine x is equal to negative cosecant plus cotangent x. Derivatives of trigonometric function. We have here the table. Functions come in pairs, sine over cos, tan over cotangent, and secant over cosecant. Derivative of pairs follow similar patterns, which functions and cofunctions switch and an extra sign. Next topic is the chain rule. The chain rule is a technique for differentiating composite function. Composite functions are made up of layers of function inside of function. The best example of this chain rule is when you are peeling onions. The chain rule is y is equal to f of g of x, wherein f is the outside function and g is the inside function. dy over dx is equal to the derivative of outside function times the derivative of inside function. The chain rule is suppose you are asked to differentiate the function f of x is equal to the square root of x squared plus 1. The differentiation formulas you learned in the previous sections of this chapter do not able you to calculate f prime of x. Observe that f is a composite function. In fact, if we let y is equal to f of u is equal to square root of u and let u is equal to g of x is equal to x squared plus 1. Then, we can write y is equal to f of x is equal to f of g of x. That is, f is equal to f and g. We know how to differentiate both f and g, so it would be useful to have a rule that tells us how to find the derivative of f is equal to f and g in terms of the derivatives of f and g. The chain rule is if h of x is equal to g of f of x, then h prime of x is equal to g prime f of x f prime of x. The chain rule deals with the idea of composition functions, and it is helpful to think about an outside and an inside function when using the chain rule. In other words, the derivative when using the chain rule is the derivative of the outside leaving the inside unchanged times the derivative of the inside. We have here the f prime of x is equal to f prime of g of g prime of x, wherein f prime is the derivative of outside function and the g of x is the inside function left alone, and the g prime of x is the times derivative of inside function. If f is differentiable at the point u is equal to g of x and g is differentiable at x, then the composite function f and g of x is equal to f, the quantity of g of x is differentiable at x, and f and g prime of x is equal to f prime of g of x times g prime of x. In Leibniz notation, if y is equal to f of u and u is g of x, then dy over dx is equal to dy over du times du over dx, where dy over du evaluated at u is equal to g of x. Reason of using chain rule. We know how to differentiate sine x and x squared minus 4, but how do we differentiate a composite like sine the quantity x squared minus 4? The answer is the chain rule. The chain rule is probably the most widely used differentiation rule in mathematics. Statement and proof. If f and g are differentiable function, then its composition function f and g and d over dx, the quantity f and g of x is equal to f prime of g of x times g. Let y is equal to f of x is equal to f and g of x is equal to f of g of x. If u is equal to g of x, y is f of x is equal to f of u. Derivative y is equal to f of x plus derivative x minus f of x. Derivative y is equal to f of g of x plus derivative x minus f of g of x, and derivative u is equal to g of x plus derivative x minus g of x. Derivative u plus g of x is equal to g of x plus derivative x. This value we put in equation 1. Derivative y is equal to f of derivative u plus g of x minus f of g of x. Derivative y is equal to f of derivative u plus u minus f of u, dividing both sides by derivative x. The proof is derivative y over derivative x is equal to f of derivative u plus u minus f of u over derivative x. Divide and multiply both sides by derivative u, we get derivative y over derivative x is equal to f of derivative u plus u minus f of u over derivative u times a times derivative u over derivative x. Applying limits derivative x as approach 0 and derivative u as approach 0. Limit of derivative y over derivative x as derivative x approach 0 is equal to the limit of f of derivative u plus u minus f of u over derivative u as approach 0 times the limit of the derivative u over derivative x as approach 0. Putting the value of derivative u, we get the limit of derivative y over derivative x is equal to the limit of f derivative u plus u minus f of u over derivative u as derivative u over approach 0 times the limit of g of x plus derivative x minus g of x over derivative x as derivative x approach 0. dy over dx is equal to f prime of u g prime of x. Putting value of u, we get dy over dx is equal to f derivative of gx, g derivative of x, proof. Next is the implicit differentiation. Explicit differentiation, you have been taught to differentiate functions in explicit form, meaning y is defined in terms of x. Examples is y is equal to 1 over x squared. The derivative is y prime is equal to negative 2x to the negative 3 power is equal to negative 2 over x cubed. Y is equal to 2x cubed plus 4x. Y prime is equal to 6x squared plus 4. Whenever you can solve for y in terms of x, do so. Implicit differentiation also, to this point, we've done quite a few derivatives, but they have all been derivatives of functions of the form y is equal to f of x, y is equal to f of x. Unfortunately, not all the functions that we're going to look at will fall into this form. Sometimes, however, you can't be written in terms of x as demonstrating the following. 2x cubed minus y cubed plus 3y is equal to 7. We need to differentiate implicitly. Remember, we are differentiating with respect to x. D over dx times x is equal to dx over dx is equal to 1. Using the general power rule and chain rule, we have d over dx times x squared is equal to 2x times dx over dx equals 2x times 1 equals 2x. D over dx times x cubed is equal to 3x squared. Simple power rule. The denominator dx and the x cubed are the variable agree. Next topic is the higher derivative. Let f of x is equal to x squared. Its derivative f prime of x is equal to 2x. If we take the derivative of the derivative again, we have that the quantity f derivative of x derivative is equal to 2. This is called the second derivative of f of x, and it is denoted as f2 prime of x or as f of 2 of x. If we take the derivative of the second derivative, again, we have that f to the second derivative of x derivative is equal to 2 prime is equal to 0. This is called the third derivative of f of x, and it is denoted as f third derivative of x or as f of 3 of x. Continuing in this manner, we define the nth derivative of f of x as f of fn of x for n is equal to 1, 2, 3, and so on. We write this as d to the nth f over dx to the n in the d over dx notation. Example, find the first derivative of f of x is equal to 2x to the fourth minus x cubed minus 2. The first derivative is f prime is equal f prime of x is equal to 8x cubed minus 3x squared. The second is 24x squared minus 6x. The third is 48x minus 6. And the fourth is 48. And the fifth is equal to 0. The derivative of a degree n polynomial is another polynomial of degree n minus 1. Continue taking derivatives, we see that the nth derivative of the degree n polynomial is a non-zero constant and that its n plus 1 to the nth power derivative is 0. If p of x is equal to ax to the n plus and so on, then p to the n of x is equal to c not equal to 0, a non-zero constant, and its quantity n plus 1 derivative p to the power of n plus 1 of x is equal to 0. Example number 2 is, find the first three derivatives of f of x is equal to negative x to the power of 2/3. The first derivative is negative 2/3 x, the power of 1/3 is equal to negative 2 over 3x to the power of 1/3. The second derivative is negative 2/3 times negative 1/3 x to the power of negative 4/3 is equal to 2 over 9x to the 4/3 power. The third derivative is equal to negative 2/3 times negative 1/3 times negative 4/3 x to the power of negative 7/3 is equal to negative 8 over 27x to the power of 7 over 3. The successive derivatives of the power function f of x is equal to x to the p in general get more complicated unless p is equal to 0, 1, 2, 3, etc. f of x is a polynomial. Derivative of logarithmic function. For the natural logarithm, ln of x is d sub x of ln x is equal to 1 over x. For the logarithmic of a different base, log a of x, d sub x of log ax is equal to 1 over the quantity ln a of x. Example, try these example problems. Find the derivative. Don't forget to use the chain rule where applicable. Y is equal to ln times 1 plus x squared. F of x is equal to ln times the quantity x to the 4th plus 5x squared to the 3 halves power. F of x is equal to 3x plus 1 times ln times x minus 1. What about ln times negative x? Consider it a compound function. F of x is equal to ln of x. Y is equal to f of g of x. G of x is equal to negative x. Apply the chain rule. D sub x of ln of negative x is equal to 1 over negative x times d of negative x over dx is equal to 1 over negative x times negative 1 is equal to 1 over x. Thus, we see d sub x times the quantity ln of negative x is equal to d sub x, the quantity of ln of x. The conclusion is we now can say that d sub x, the quantity of ln absolute of x is equal to 1 over x. D sub x, the quantity of log a absolute of x is equal to 1 over the quantity ln a times x. Apply to finding these derivatives. Y is equal to ln quantity negative 4x. Y is equal to log 5 square root of 5x plus 2. F of x is equal to square root of ln absolute x minus 3. The last topic here is the rates of change, the application related rates. Procedure for solving related rate problems. First is assign symbol to all given quantities and quantities to be determined. Make a sketch and label the quantities if feasible. Number 2, write an equation involving the variables whose rate of change either are given or are to be determined. Using the chain rule implicitly, differentiate both sides of the equation with respect to t. Substitute into the resulting equation all known values for the variables and their rates of change. Solve for the required rate of change. Related rate problems are differentiated with respect to time. So, every variables except t is differentiated implicitly. Example, two rates that are related. Given y is equal to x squared plus 3, find dy over dt when x is equal to 1 given that dx over dt is equal to 2. Y is equal to x squared plus 3. dy over dx is equal to 2x dx over dt. Now, when x is equal to 1 and dx over dt is equal to 2, we have dy over dt is equal to 2 times 1 times 2 is equal to 4. Next example is, a pebble is dropped into a calm pond, causing ripples in the form of concentrating circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When this radius is 4 feet, what rate is the total area A of the disturbed water increasing? The given here is dr over dt is 1. When r is 4, what is dA over dt? Given equation, the area is equal to pi r squared. Differentiate dA over dt is equal to pi r squared dr over dt. dA over dt is equal to 2 pi times 1 times 4 is equal to 8 pi. That's all for today. Thank you for watching. Bye.